Well, good afternoon, and welcome to NASA headquarters in our nation's capital. I'm Dwayne Brown from NASA's Office of Communications. Following the July 14th historic Pluto flyby by NASA's New Horizons spacecraft, the research team has begun sharing the unprecedented images and science findings with the world. And today, they have more. Ladies and gentlemen, this mission has clearly been embraced by the entire world of all ages. In fact, the numbers that are coming in with multimedia, social media, the internet, radio, TV, is in the billions. We also want to give a NASA headquarters shout out to the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland for the unforgettable moments at their facility this week. And we have now transitioned here to NASA, where the future media briefings will be here. We'll have brief presentations, and then we'll open it up for questions starting here, our NASA centers, social media, and the phone lines. Social media is absolutely exploding with this mission. Follow the conversation at #PlutoFlyby, Twitter, Facebook, YouTube, and other NASA accounts on that. And if you have questions, send them in at #AskNASA. And certainly all the information you have been hearing, will hear today, and in the weeks and months, will be online at www.nasa.gov/New Horizons. Let me introduce you to today's participants. First up, Jim Green, Director of Planetary Science Division at NASA headquarters. Alan Stern, New Horizons Principal Investigator at the Southwest Research Institute in Boulder, Colorado. Randy Gladstone, New Horizons co-investigator at Southwest Research Institute in San Antonio. Fran Bagenal, New Horizons co-investigator, University of Colorado, Boulder. And Jeffrey Moore, New Horizons co-investigator at NASA's Ames Research Center in Moffett Field, California. With that, turn it over to you, Dr. Green, to kick us off.
Thank you very much, Dwayne. Today we're going to talk about some of the fantastic discoveries about the heart of Pluto. But before we start that, what I'd like to do is really talk a little bit about the heart of the New Horizons mission. First, I want to thank APL and SWRI in particular for all the work that they've done making this mission happen. There's a whole series of contractors, our industry community, that's really made this mission the spectacular success that it is. APL hosted a fabulous historic event this week that many attended personally, but millions attended virtually, which has really been captivating. What a historic week. In particular, the heart of New Horizons that's beating and beating well and beating still was put on and produced by the Department of Energy, one of our major government partners, and that's with its radioisotope power enables us to move further out into the solar system, and it's on a trajectory to leave. Well, currently, if I can have our first graphic. Here we see New Horizons past Pluto. This is through the ISON solar system that you can get access to through the web. And as you can see, it's more than 2 million miles away from Pluto. You know, for 10 years, or nearly 10 years, the New Horizons team, we're always talking about each day we're closer to Pluto. Well, now each day we're further away from Pluto. But here's where it comes in that's important to remember, and that is it's during this time that we're going to be able to obtain the data from the flyby. Right now, we've only received 1 to 2% of that data on the ground. By next week, we'll have perhaps as much as 5 or 6%. And so some of the discoveries that you're going to be hearing about today has only been the tip of the iceberg and the few percent that we were able to get down since the encounter occurred on Tuesday night. And so without further ado, let me turn it over to Dwayne to introduce our next speaker.
And Alan, go for it. All yours.
All right. Hey, that was
Someone who doesn't need an introduction.
Fantastic. Well, we're really happy to be here, and I want to say on behalf of our entire team, we've just had the most fun communicating about exploration and about just how exciting solar system exploration is this week. But I think Pluto's becoming a brand. It sort of sells itself, and we don't really have to work all that hard. I do want to recognize the team members who are here. We have quite a number of members of the New Horizons mission team. If they would stand up to be recognized, if you're working on New Horizons, thank you very much. We also have, and I'd like you to recognize some New Horizons mission educators who are in the audience. If you'd stand up to be recognized. And then finally, I'd like to recognize one of our science team collaborators who's come over from Europe to help us work with the data a little bit. Some of you may know Dr. Brian May. Right?
You hear me? Probably not. I'm one of those people in Europe who's been following your every moves on our laptops and TVs in our offices and in our bedrooms. It's a thrill to be here with you, and what an amazing achievement. You have inspired the world. Thank you.
Thank you. Well, while you enjoy this beautiful eye candy, the Pluto Charon system is revealed by New Horizons in color. You really see a binary planet. Enjoy that view while I tell you a little bit of news about New Horizons. The spacecraft is doing very well. As Jim said, we're now a little over 2 million miles on the far side of Pluto. Spacecraft's performing according to plan. We exited the 9-day close approach encounter load just yesterday. We're now in the first of our departure science load. So we're looking back at the planet in that special geometry, looking at the night side, and doing various experiments and splitting our time also downlinking data. And we have been downloading a lot of data. So we have some big news, and I expect we'll have more big news next Friday when we've downloaded even more. I'll have to tell you, I'm a little biased, but I think the solar system saved the best for last. So I'm going to show you some things, and if I can have my, I'm going to start off with a little news, and then I'll pass it along to my colleagues. If I can have the next time step, the next graphic, let's see if we can bring that up. There it is. Okay, that's not very many pixels across, but that's Pluto's satellite Nix in its first well-resolved image. Now, let's set our expectations properly. As little as 3 months ago, we didn't have pictures of Pluto this good. And this is actually about twice as many pixels as the best Earth-based views of Pluto. We were able to determine Nix's size, about 25 miles across. We're able to measure its brightness. It's intermediate in brightness between Charon and Pluto. In this view, we believe we're looking roughly down the pole of an elongated object, not as elongated as this pin. It's about twice as narrow in one direction as it is long, and we're kind of looking down the barrel of it right there. We'll have more to say about Nix when we get more imagery on the ground, but a fascinating satellite. And I'll move to the next time step. This is a overlay of some data from the Ralph instrument, from the composition mapping spectrometer, that for the first time identifies the location of a carbon monoxide-rich region on Pluto that had been observed from Earth for quite a long time. But now we can actually overlay it on a map. So that's a New Horizons map product overlaid with contours for the abundance of this carbon monoxide. And you can see that the peak is on the western side of Tombaugh Regio, or the heart. Very nice to be able to do that. Now, you can see it's pretty concentrated spatially. We're not sure we understand that. understand the origin of that. It could be that there's a source region there, and we'll be looking for it hard in high-resolution imagery, or there could be another explanation, but either way, it definitely catches our eye because across the rest of this disk, there's no other carbon monoxide concentration, anything like this. We already know that. So it's a very special place on the planet. Randy will shortly show you some pretty profound results concerning the atmosphere. In fact, the first results that we'll share with you about the atmosphere, and Fran will show you the detection of escaping ions from Pluto made by our plasma instruments. And then Jeff's going to talk about new terrains imaged at high resolution. I'm going to give you a little preview of that. So if I can have the next graphic, have a look at the icy, frozen plains of Pluto. Who would have expected this kind of complexity? And by the way, this scene is essentially adjacent, neighboring the mountain ranges that you saw a couple days ago. So we can see that there are stark contrasts on Pluto in terms of the geology. Jeff will show you a lot more of that, but I want to show you something else. I'm going to show you a graphic. It's a flyover made as if your eye was 25 miles over Pluto, and we can go ahead and start that. A flyover of faraway mountains and plains in the Kuiper Belt. If they can go ahead and call that up, I think you'll enjoy seeing it. If we can lower some of the, probably can't lower house lights given the television. Is that graphic available, the animation?
It's being shown.
There you go. We can't see it back here. There it is. Yeah. What you're looking is a scene that's about total width about 250 miles across, 400 kilometers. And these mountains soar as high above their local terrain as many of the mountains in the Rocky Mountains do here in the United States. Pretty impressive. The second flyover is of the plane that I just showed you, which we're informally calling Sputnik Planum. Well, Sputnik was an explorer too. This scene is just as wide, 250 miles across, gives you a feel for the scale of the features that you were looking at. Really beautiful, beautiful surfaces, and we're going to be seeing a lot more of this. This is 400 meter per pixel imagery, and by next week we'll have more than twice as much as the 3 frames that we've already been able to share by the end of today, and we'll share that with you as well, covering a lot more terrains. I think with that, I'm going to turn it over to Randy Gladstone to tell you about some early atmospheric results. Randy.
Okay, thanks, Alan. If we could go to the first time step, and I'll show you what the atmospheres team is looking at. We have had to wait until we got past Pluto, and we're looking back towards the sun to get our best data set. This shows you on the left an animation of what it's like when the Pluto goes in front of the sun as seen from the spacecraft. And the curves on the right show you 2 plausible atmospheric models for Pluto's atmosphere. And here we show you the data that we got coming down. And it's just count rate data. Each one of those points is 10 seconds, but we get, for every point on there, we'll get a whole spectrum. And then on the way out, if we flip it, you see the green line goes back exactly the same spot. So the atmosphere is very symmetric on opposite sides of the planet, and it seems to be more consistent with the red line, which is a more sluggish atmosphere or stagnant atmosphere. So we've already eliminated, just from this little bit of data that we got, a glimpse of the data tells us, or eliminates a couple of models that were contenders up till now. So the next slide shows you, that was zoomed in at just the surface of Pluto, but we see the atmosphere way far out. So this is how our count rate went from the beginning on the left to the end on the right in the red and white curves, and Pluto's shown there in the middle. So we see the atmosphere all the way to the ground. From Earth, that inner circle around close to Pluto is the limit, the highest the stellar occultations from Earth can see, and they can't see to the ground. They can only see to 30 miles above the surface or so, out to 170 miles. We see from the ground out to 1,000 miles above the surface. So you can see this isn't a straight, simple curve. It drops slowly, and then it picks up, and then it has another bend where it picks up again. At the highest altitudes, that's nitrogen, molecular nitrogen, the main component of Pluto's atmosphere, starts to absorb the sunlight. And then lower down, methane kicks in, and then even lower down where it gets steepest, that's heavier hydrocarbons near the surface that are absorbing the sunlight. So like I said, each point on this graph will be a whole spectrum of colors in the ultraviolet light that we're getting this signal from. And we're really looking forward to getting that data in a month or two. So, but it's very tantalizing right now, and it already is, we're able to do science with it. But that nitrogen atmosphere, because Pluto's so small, it escapes directly into space, and Fran is going to tell you what it does out there.
So we've had 9.5 years of this flight out to Pluto to think about what are we going to see with the plasma instruments. And we are seeing all sorts of things. We haven't got all the data down yet, of course, like all the other instruments, and we're really looking forward to getting it down. But in the meantime, let me tell you a little bit about what we think is happening. So Randy has already discussed that we know the atmosphere is nitrogen, and we suspect it's escaping because of the weaker gravity on Pluto. It's about the gravity is a lot weaker than Earth and than Mars, and so we know that it's going away. And what we think is happening is that the solar wind that comes from the sun, the protons and electrons, charged particles that are streaming out at supersonic speeds, will eventually crash into. They'll interact with this escaping atmosphere, and that this will then produce, we suspect, a shock upstream. Maybe it's not quite so stark. There's some. We know that there's an upstream amount of nitrogen ions. We've already observed that with New Horizons, with the PEPSI instrument, well upstream, and that was energized by the solar wind and carried away by the solar wind. But the real question is what happens as it interacts with the denser escaping atmosphere that Randy was talking about. And so what happens is, and this graphic that you're looking at here gives you a sense of what we think's happened, is that as it escapes, the atmosphere is ionized, it's picked up by the solar wind, and the size of this interaction region actually fills out beyond the scale of the satellite. So it's a large volume. Now, we have actually flown through this with the instruments, and the next slide will show you what we think is happening, is that SWAP now has actually detected the ionized atmosphere. These are nitrogen molecules that are being ionized by photons, UV photons from the sun, and then once they're ionized, they get entrained in the solar wind and carried away. And so what we see behind Pluto is a tail, an ion tail of this ionized escaping atmosphere that's being pulled away and carried away in the solar wind. Now, when we get the rest of our data back in August or so, we really will be able to quantify, when we add the data that Randy and the atmospheric team put that together with the SWAP and PEPSI observations, we'll be able to quantify the amount of that escaping atmosphere. What we think it is, based on models and a pretty good guess, is about 500 tons per hour of material that is escaping. And this is, for comparison, we know that the escaping atmosphere for Mars, which is being studied by NASA's MAVEN mission, is about 1 ton per hour. So this is substantially more because of the weaker gravity on Pluto. Now, what is the consequence of that? Well, if you add that up roughly over the age of the solar system or the age of Pluto, this is going to be equivalent to something on the order of 1 to 9,000 feet. So that's a substantial mountain of ice, nitrogen ice, that's been removed through this evaporation and then escape into the atmosphere. And Alan Stern has worked with Simon Porter and Amanda Zangarian predicting what this will do to the geology, and they have a prediction paper, but Jeff and the geologists are going to look at the geology and tell us what actually happens.
Indeed we will. Well, I'm still having to remind myself to take deep breaths. I mean, the landscape is just astoundingly amazing. In fact, let's go back to this picture that we talked about a few days ago when it was still a global view, and remind ourselves that the global view shows some surfaces on Pluto are peppered with impact craters and are therefore relatively ancient, perhaps several billion years old. Whereas other regions, such as the interior of the heart, which we've now named Tomball Regio, show no craters at all, are thus obviously younger, and indicate that Pluto's experienced a long and thus all of this suggests that Pluto's experienced a long and complex geological history. And so this means that there are active landform creating processes operating into the geological current times. Now, some of the craters appear partially destroyed, perhaps by erosion. And there are also hints of parts of Pluto's crust that have been fractured, and thus that indicates there's probably been some forms of tectonics. Now that we've seen mountains, I think there's pretty obviously mountain-building forces operating on Pluto. And also, some of the higher resolution images, show that there are craters which may have been partially eroded away. So erosion processes also seem to be operating on the surface of Pluto. And then, may I have the next time step, please? Next slide, please. So let's zoom into our 3-image mosaic of the 400 meter per pixel imaging that we've taken. And here you can see there's the provinces of the 2-mile-high mountains, which we're now calling Norgay Montes, which are located in the lower left. There is extensive large-scale pitting, you can see in the lower right. And then there is this extremely young plains, which makes up the northern half of the upper half of the image. And by the way, this image is oriented so north is up. Being a geologist, I kind of like that. Makes life easy. And this is just a taste of what I'm sure is in the unsent data. So may I have the next slide, please? And so you see there's the names that we've assigned to them. As Alan mentioned before, we decided to name Sputnik Planum after the first artificial satellite launched into space, and thus beginning the space age. And Norgay Montes, of course, is after the Nepalese Sherpa who went up the Mount Everest with Edmund Hillary, and is the first Nepalese to have a name on any planet in the solar system. Okay, let's have the next time step, please. Okay, let's look at this little region here in the middle of Sputnik Planum. May I have the next time step, please? Okay, when I saw this image the first time, I decided I was going to call it not easy to explain terrain. So this is the frozen plains of Pluto. So when you look at this plains, you can clearly see that we've discovered a vast craterless plains that has some strange story to tell. For convenience, as I said, we've tried to think about in various types of geological metaphors, which I'll get to in a moment. But judging from the absence of impact craters, it's clear that Sputnik Planum, couldn't possibly be more than, let's pick a round number, 100 million years old, and possibly still being shaped to this day by geological processes. So this could be, only a week old for all we know. In this image, you can see things as small as about a half a mile across. And then let's talk about some of the things we see in this scene. So let's go to the next slide, please. The surface is broken up into polygonally shaped segments, which you see are listed on this slide as irregularly shaped segments that are roughly 12 to 20 miles across. They're bordered, as you can see, by what appear to be shallow troughs. Some of these troughs have some darker material that seems to be in them. I don't know if that's material that's collected there or erupted there. I don't know, but some of the troughs do have what appears to be just dark stuff. Much more enigmatic are these clusters of hills, which I think you can see pointed out in the upper right of the frame. They appear to be elongated clumps of mounds, and they trace out the shapes of the troughs that encircle the polygons. About the only thing we can say about the hills, except for their smoothness, their mound-likeness, is that the hills are higher than the surrounding terrain. We don't have a value for that yet, but this is part of a bigger stereo mosaic sequence we took. So when we get all the data down, we can tell you exactly how high they are and exactly how they're shaped, which will go a long way to help us interpret what, in fact, created these hills. We have, and thinking of the hills, we suspect that either the hills may have been pushed up from underneath along the cracks, but alternatively, a completely different explanation is that they are erosion-resistant knobs that are standing out as the surface is being massively eroded and lowered. So we don't know which of those two explanations is correct, but you can see that we can go either way. They can either be popping up or emerging from a erosion lowering process. It's lowering the entire plains. In the terrain in the lower right, I think you can see there are several of the polygons appear to be etched by fields of small pits. Now, while this identification is a little tentative because there are still compression artifacts in this first batch of data, which has been sent down to the ground with velocity compression, we will very soon receive these same images without any compression. And I think the issue of whether that is indeed vast scenes of pits will be verified probably pretty straightforward way. Similar features to these vast pitted surfaces can be seen, for instance, on the surfaces of glaciers here on the Earth. And on terrestrial glaciers, this is caused by erosion from wind and sun. But on Pluto, the erosion mechanism would have to be a process called sublimation, which is when the ice turns directly from solid to gas in the way frozen carbon dioxide or dry ice does on the Earth. So what do these features tell us about Sputnik Planum? One possibility out of many is that the polygons are signs of convection occurring within a surface layer of carbon monoxide, methane, and nitrogen ice, driven by the modest heat from the interior of Pluto itself, creating kind of the same sorts of patterns you see when you look at the surface of a boiling pot of oatmeal or like the blobs in a lava lamp. But alternatively, these polygons could be analogous to mud cracks, and they could be created by the contraction of the surface materials. But we have various ways to test those ideas, which we'll be using and reporting out in forthcoming conferences and scientific papers. And as I said before, we will learn more about these enigmatic features and terrains and much higher resolution and stereo coverage, which is still up on the spacecraft and going to come down in the next few months. And in fact, I think 20 years from now, people are going to look at the coverage we have of Sputnik Planum in particular and think we planned the whole encounter around looking at Sputnik Planum. But that's just a pure coincidence. It just worked out that way that the fates of space exploration, favor us to put some of those interesting places, directly in the sites of our highest resolution, highest quality data. So this is going to be really fun. Okay, so to be a little more speculative, we also saw one other thing. So I have the next slide, please. So let's zoom into this area that's just northwest of the one we just looked at. There you go. Okay, so these dark smudges appear to be aligned and running from upper left to lower right and may have been produced by winds blowing across Pluto's icy surface. May I have the next slide, please? And so on Mars and Earth, similar features are what scientists call wind streaks and are produced when prevailing winds cause erosion or deposition, we're not sure which of those, material behind topographic obstacles. And don't ask me what the topographic obstacles are because we can't quite tell yet, but we will be able to tell you when we get the rest of our data down. But alternatively, and this is even more speculative, they may be plume deposits associated with glaciers, like those seen on Neptune's icy satellite Triton. The plumes themselves, if they exist on Pluto, have not been spotted yet. So this is not an announcement we've spotted plumes or geysers or anything like that on Pluto. But of course, we will be looking for them in images yet to be received from the spacecraft. So, let me conclude by saying these are the early days of the post-encounter analysis. And as extraordinary and provocative as these images are, we are in the most preliminary stages of our investigations. And we're still entertaining, as you can tell, the widest range of hypotheses. We are acutely aware that jumping to conclusions comes at great peril. So with that caveat, I am going to pass it back to Dwayne.
Thank you all. Let's give this team a round of applause. Much, much more to come. Okay, now we transition into the Q&A. We're going to start here at NASA headquarters with the media and the audience. Then we're going to see if we have any questions from our NASA centers, phone bridge, and of course, social media. So if you can wait for the mic, raise your hand. Do we have any? If we have And give your name and affiliation, please.
Stephen Young with Astronomy Now magazine. For Alan, we heard about how this is just the tip of the iceberg, and also in these images you can see they're compressed. Can you quantify how much data you've got on the ground right now versus how much is on the spacecraft waiting to come down? And what's the difference going to be in those images when we see the uncompressed versions?
Yeah, I'll be happy to. So we have about, in very round numbers, about 50 gigabits of data that was made beginning about 10 days before closest approach. And by the way, that 50 gigabits is the full amount that we will store through the end of this month as we look back on the system. So that includes data we haven't quite yet taken. All that will ultimately come to the ground with lossless compression, about 2-to-1 compression that doesn't introduce any source of noise. But our lossy compression can accelerate our ability to get data to the ground with the expense of some noise. Some scenes will compress 10-to-1 or even better. So it's a very efficient process at the beginning of the downlink to send home what we call the browse data set. The concerted effort to get everything to the ground that can be compressed will begin in September. And that will take about 10 weeks, maybe 12 weeks, depending upon DSN schedules and other factors. We currently have on the ground less than one of those 50 gigabits, probably around 1 gigabit. I didn't check this morning. We can get you a more accurate number if it's helpful.
Eric.
Hi, yeah, Eric Hand with Science Magazine. My question's for Randy. You mentioned that you think you've ruled out this turbulent model for the atmosphere and that you think it's maybe more sluggish or stagnant. What are the implications of that for transport of materials around the planet via frost? And does it have any effects on maybe what you're starting to see on the surface with these wind streaks? Is this an atmosphere that blows around all the time, or maybe not so much?
Yeah, good question. We still don't have a good measure of the lowest atmosphere, where it's very complicated. The atmosphere, we think of all the atmosphere on Pluto is sort of compressed into a very thin layer near the surface, where the winds can be up to a few meters per second easily, and those numbers are good enough to launch or loft particles off the surface, micron sizes. So it's not inconsistent at all, even with the sluggish atmosphere, to be able to move stuff around still. So we think it's fine, or consistent so far.
Frank?
Frank Mooring with Aviation Week. At this point, have you learned anything that will help you understand what happens to the surface of Pluto as it goes through its long orbit?
Good point.
Anybody else can chip in. So we've understood the physics of volatile transport coupled with atmospheric escape very well for a long time, but we haven't had the boundary conditions to be able to really run those models in a way that we'd like to, because we don't know, for example, we haven't known until now the details of where the bright areas are, where the darker ones are, and that can relate to the way that areas heat up, particularly those places that might be devoid of volatiles and would have higher swings. So in the coming months, we're going to see composition maps, albedo maps, topography maps, and some thermal maps come to the ground, all of which will make tremendous input to be able to inform us how to run those models for the real Pluto. And we're really going to be living in a very data-rich environment, because New Horizons payload was selected to be able to make comprehensive answers about those kind of first-order questions. Because Pluto's orbit is elliptical and the planet's pole vector is tilted over, its obliquity is very high, even higher than Uranus's. It's a pretty complex situation. We know how to model it, and once we get this data on the ground, I think we're going to get some spectacular results. It'll show us not just what happens, Frank, around a 248-year orbit, which itself is pretty interesting, but over much longer timescales. I, for example, am very interested in how the volatiles transport over long times around the planet, and whether sufficient material moves around the planet to actually, or to potentially, bury structures or be removed from structures so that we see them. at different times in Pluto's seasonal cycles. The climate cycles have very long periods in some cases. Everybody's aware of the 248-year orbital cycle, but the pole vector actually circulates over a 4 million year cycle, which averages over many, many orbits. So running these models is going to be fascinating, and we're going to have the data on the ground to do it. I think we'll really hammer the nail on the head.
Okay, as we're going to come back, I'm going to go to the phone lines. And for the media, like we've had at all of our briefings, there are lots of media from all over the world. They're going to want to try to ask questions. I want to try to get to as many of you as possible, so please limit your questions to one. So we're going to go to phone lines, we're going to go to social media, and then we'll come back here. So on the phone line, up first from NBC News, Alan Boyle.
Oh, thank you. This might be for Jeff or for Alan. Just looking at that hillocky terrain and the potential for plumes, can you say anything further about whether this is Triton-like terrain? What sorts of similarities do you see to what folks have seen on Triton, and how do you hope to resolve the issue about those plumes or wind streaks?
Well, first of all, as I said before, we are not making an announcement that we've seen plumes in any way. As far as trying to compare it with Triton, well, the sad story for Triton is it didn't have a New Horizons encounter. The data set we have for Triton is about twice as, well, let me put it this way. The very best images we ever took of Triton under the best of circumstances are only just as good as the pictures we've shown you so far. And almost all of Triton was imaged at much worse resolution than the images that we've shown you. And our images, in contrast, these are just kind of the middle resolution pictures for us compared to the really good stuff we haven't even seen yet. So part of the problem, it's hard to compare Pluto with Triton in some sense because we need to see Triton better. Having said all that, not only did people see active plumes, did the scientists in 1989 see active plumes on Triton. Triton appeared to be covered with a number of just what looked dark aligned markings, which were interpreted as wind streaks. And so to the extent that we can compare our good data with Triton data, and the best Triton data was not actually over their wind streak terrain, we think they are comparable. I'm sorry that was a long explanation, but that's kind of where we are.
Jeff, it's probably worthwhile for you to speak to the comparative differences to do with our detection of mountain ranges right off the bat and the polygonal terrains.
Well, right. I mean, for one thing, as people have, for many years, since the 1970s at least, wondered whether these very evolved young terrains you see on the giant icy moons of the gas giants were made that way because of a process called tidal heating, where the moons interact with themselves and with the body that they're orbiting around to basically heat up their interiors through friction. And so when people see like Io's volcanoes erupting, Io's a volcanic moon of Jupiter, they are attributed to this process called tidal torque heating. But the question was, could icy worlds, minding their own business, not orbiting some giant planet, also be geologically active? And the answer is obviously yes. Pluto is every bit as geologically active as any place we've seen any place else in the solar system. And this really does answer sort of a fundamental question about, are ice worlds able to do their thing in their own right, and or are they dependent upon the help of the big planets they orbit around?
Next up, Pete Spots, Christian Science Monitor. Pete?
Thank you very much. And I think this is for Dr. Moore. One of the detailed question when you were talking about the height of these hills inside these trenches as being above the surrounding terrain, does that, just to be clear, is that the terrain trenches or the actual interiors of the polygons? And do you have any sort of depth estimates for those troughs and any sort of ballpark estimates for the heights of the hills?
Okay, well, the height of the hills appear, and we don't have any quantitative data to say much more than this, appear to be a little higher than the surface represented by the polygons. We don't have any direct measurements of shadows and so on. As I've said before, we will be receiving data that's 6 or 7 times higher resolution and in stereo. So, there's hardly even any point in speculating too much about the height of the hills, and we can give you the answer explicitly very soon in the next few months.
Next up, Ken Kramer, University Today. Ken?
Congratulations, great results. I think my question also is about these polygons. I wonder, that Phoenix landed on polygons a few years back. I wonder, is that a reasonable comparison at all? Is there any relationship to them at all, or are they totally different? Thanks.
Well, you are right that when you look at large polygons elsewhere in the solar system, the surface that is most reminiscent of the surface we are looking at is the high altitudes, the high latitudes of the northern hemisphere of Mars. And indeed, the Phoenix lander did land on such polygonal terrain near the Arctic of Mars. Having said that, as I said earlier, that we were really entertaining two alternate explanations, and I think right this second we may weakly favor the science team, the geology team may weakly favor the idea that some form of internal convection may be responsible, but as I said, we're still very, very open to the idea that these could be due to contraction, and it's contraction, thermal contraction, that forms the polygons, is essentially responsible for the polygons on Mars, that in combination with sublimation. So they could be more, the process could be more analogous to the processes operating on Mars. It's just really too early to say.
1 second. We're still on the phone line. We're going to do 3 more calls from the phone. We're going to go to social media, and then we're going to come back here for the media and the audience. So next up, Dave Mosier. Hope I got the last name right, from Business Insider. Dave?
Yeah, thank you. Congratulations on the mission. This is for Jim, maybe for Alan. You mentioned the beating heart of New Horizons. There's only so much of that key material left, plutonium-238. I'm curious, what is the status of efforts to make plutonium-238, and how is the current supply crunch limiting future missions NASA is dreaming of?
So currently we have our plutonium is being, of course, managed by the Department of Energy. We do have a fair amount of it. It's approximately 17 or so kilograms of plutonium that is available to us that could be used right away. We have additional plutonium. Doesn't have quite the energy density we need to actually use in these missions, but we've also been given the approval by Congress and support by the administration to be able to start generating plutonium-238, and that's really good news. The Department of Energy has created a process that has, and they've verified it, to take neptunium, irradiate it with neutrons in some of their reactors, and the reaction ends up providing one of the byproducts, plutonium-238, and then that's can be extracted and then stored. So right now, we feel really good that we're in the position to be good stewards of the planetary program for many decades to come. We have adequate reserves of plutonium on the ground, and indeed we'll be making it starting late this decade, early next, on a regular basis.
Kelly Beatty, Sky and Telescope.
Thanks very much, Dwayne. I'm afraid I'm going to jump ahead a little bit in the playbook. For either Alan or Randy, do you see anything in the ALICE or REX data, occultation data sets to suggest that Charon has an atmosphere?
Well, I'll speak to that. We don't have those data on the ground yet. They'll be coming down, I believe. Is that right, Randy, in the next 3 to 5 days? Yeah, Sunday. So we'll get back to you on that.
Soon.
Okay, last question before we go to social media from Mike Wall, space.com.
Thanks, guys. Yeah, this is just a quick one about how, like sort of old all these terrains are. Do we know enough about like impact rates, cratering rates out there in the Kuiper Belt to kind of make some guesses, even on the terrain where there are craters, or are cratering rates out there lower than they are and sort of like closer to the sun, and like is it a totally different ballgame out there?
Well, the way we estimate that is several ways. First of all, we have seen cratered surfaces on the moons of Uranus and Neptune. We can obviously study the larger components of the Kuiper Belt down to a few tens of kilometers across with Hubble and other telescopes. And so by looking at the cratering records on the moons of Uranus, Neptune, and even Saturn, and looking at the numbers and objects and distribution of objects in the Kuiper Belt, there have been several studies which have derived an approximation of what the crater flux rate is. So it's far from a precise number, and we can often tell you if a surface is extremely old or extremely young. It's actually harder to tell you if it's an intermediately aged surface. Then you typically have factor of 4 uncertainties in those. But we think we understand the cratering rates well enough to say that if you see a surface which has no craters, it's difficult to understand how it could be much older than around 100 million years.
Okay, as I said earlier, the world has embraced this mission with billions, and social media is certainly a big part of that, and NASA is always looking to reach out to new audiences. So we're going to see what the world is talking about on social media with Jason Townsend. What's out there in the world?
Sure. Our first question here comes from Twitter user Brianna, who asks, how do we know Pluto's atmosphere is escaping? How is that measurement made?
We have not yet actually measured the escape. Okay, we hope to. Currently, it's based on expectations, understanding the gravity of Pluto, that it's relatively weak, and that we expect it to be escaping. Furthermore, we know that there's a little bit of methane, and maybe Randy can tell you a bit more about that, but we know there's methane in the atmosphere, and we all know from Earth that methane is a greenhouse gas that absorbs sunlight. And so that heats the atmosphere, and it's the energy deposition of sunlight into the atmosphere that gives it that energy to escape the gravity. So we're pretty sure that that's happening. We haven't got a direct measurement, but we will, by August, have measurements from both SWAP and Pepsi that will tell us, quantify the amount of escaping atmosphere, which will compare with the atmospheric observations coming from the ALICE and REX teams.
Next question comes from Twitter user Jason, who asks, what sort of material could be responsible for Pluto's dark stains? Organics?
Jeff, do you want to speculate?
Sure. Why not?
I don't.
The least crazy idea, which I think we're still working on, I know that this will hopefully be determined with the spectrometer, with the LISA instrument, is that those dark stains, well, the composition of the dark stains are probably just higher hydrocarbons made by the irradiation of methane. And the methane basically can be either irradiated on a surface ice, or it can be irradiated more likely and more commonly as particles high up in the atmosphere, and they simply very slowly rain down to the surface. And for instance, the streaks, that they in fact turn out to be wind streaks, are probably just these very fine particles that sort of slowly fall out of the atmosphere and collect on the ground, and the wind sweeps them along, and they get caught behind wind traps, behind obstacles, and they're downwind of the prevailing winds.
Let's take one more, and then we'll come back here, Jason.
All right, lots of questions about elevation here. This one comes from George, who says, will the data collected from New Horizons be sufficient to create Pluto and Charon elevation maps?
Absolutely. Absolutely so, for both encounter hemispheres. So for the surface you can see pretty much in the picture on the screen, it's still up on the screen now, we will have, although they will always be at the same resolution, topographic maps for the near encounter hemispheres of both worlds.
Okay, and I want to thank our social media audience, and we're going to answer those questions, get them in at #AskNASA. We have scientists, and we'll get to those answers as quickly as possible, but you can follow the conversation, and those answers will probably be on that conversation. There's a lot of conversation at #PlutoFlyby. So let's come back here. Let me see your hands high here. Let's go here, and then we'll work our way this way. Name and affiliation, sir.
Thanks. Stephen Clark with Spaceflight Now. I know you're not prepared to make an announcement about geysers or plumes. Do you need a direct detection of that, or is there some indirect way you can find some evidence on the surface or in your thermal maps to say you found them?
There might be some indirect means, but I'm an old-fashioned geologist. I wasn't quite born in Missouri. I was born in a state near it. I want to see, unambiguous evidence that something's, erupting up into the atmosphere, and we see it. Don't worry, we'll come and tell you about it.
Emily Lochtawala with the Planetary Society. Alan, for a long time you've been a proponent of and been supported by the amateur image processing community, and you started releasing the raw images. The raw image release was halted this morning. I'm wondering if that is a plan to continue, or if you are going to keep the data in order for the scientists to interpret it before you show it to the public.
Yeah, we intend to continue to release all the LORI images. However, as we're winding down from the peak of activity after the intensive flyby activities, we're going to move to weekly releases all in one set. That's a manpower thing, and it's also helping us vet the images when we don't have the entire science team assembled. The data is really going to start to flow in the fall. And before that, after the next week or so, one of the things we want to make sure the amateur community knows is that we're going to turn to getting the plasma data and other what's so-called low-speed data sets to the ground. So there'll be a long gap. It's not because we're stopping the sharing. It's because we're not sending imagery to the ground in the month of August and early parts of September. Then we'll start again, and as I said, we'll be on a weekly basis, and you'll be able to count on it like a clock.
So we're going to take a few more questions, then we're going to close out. Leo?
Thanks, Dwayne. Leo Enright with Irish Television. We journalists absolutely love flybys, mainly because it's science at the speed of journalism. And who could possibly not like that? But if you'll forgive me, I didn't want this week to fly by without remarking that this is the first planetary flyby in American history where the imaging specialist Yuri van der Woody has not been intimately involved in distributing the imagery. Yuri was the sixth person at the front table at every flyby. We completely relied upon him to provide us with imagery during those days. Yuri, I don't know if it was something about us journalists, but NASA chose an Air Force pilot, fighter pilot from the Dutch Air Force to deal with us. But he was our link with the imaging teams for my entire professional career. And I didn't want this week to pass without mentioning Yuri. He was a great public servant. He was a terrific guy. And I suppose, as we in Ireland might say, he was a mensch.
Yeah. Well, he was a really great guy. Even when I was a young student, you could call him, he'd pick up the phone, you could say, "Hi, I'm so-and-so from Pauls Valley, Oklahoma," and he would mail you pictures of the latest encounter. It was fantastic.
Yeah, and for our television audience, Yuri, I knew him, but we also had some unfortunate folks that passed during this time. That the NASA family, ladies and gentlemen, we work very hard, but we care for each other very hard, and we've lost some people, Yuri and others at the Jet Propulsion Lab. So our thoughts and prayers go out, but the NASA family cares very hard when we lose folks. Okay, Eric, and then we'll take one more, and then we'll close out.
Eric Han with Science again. Maybe we can bring up that image of the carbon monoxide-rich terrain in the middle of the heart. I'm wondering if you can tell us how thick it is. Is this more than just the veneer that you suspect everywhere else? Is it pure? Are there other ices mixed in? And then how did it get there? Is this something that was deposited from above, or could this be something welling up from within? And even if you can't say right now, how would you approach distinguishing between those two things?
Gosh, go ahead.
All right. I'm going to say a couple words about that, and we specifically brought along our composition team lead, Will Grundy, who's down in the audience, who has a microphone, because we thought we might get a question about that, and his team led the work. We know that what we're looking at is at least thick enough to make that absorption. It's at least the veneer, but it could be quite a deep layer. Will?
Yeah, you said it exactly right. You only need a centimeter or something to produce an absorption of that depth. So we know that there's a lid that includes a lot of carbon monoxide, but how that interacts is potentially quite subtle. It is soluble in nitrogen ice, which is also widespread around the surface, and methane is also partially soluble in that mixture. And so how they combine, we really don't know yet, and we're going to have to do some detailed modeling. I like the scenario of it upwelling from below, but I don't think we're anywhere near proving that that's what's happening.
Last question.
The Planetary Society, it's for Randy. I'm just wondering if you can tell me if you see any signs of atmospheric structure in your occultation yet?
Yeah, those kinks that you saw in the occultation profile tell us where one atmospheric species is absorbed out and the other one takes up. So that's not really structure, but just from the shape of those profiles, we know how extended the atmosphere is. It actually might be a little cooler than we thought, but we'll get that later.
Okay, well, ladies and gentlemen, folks watching from all over the world, the Pluto story is just beginning. You can follow the conversation on all the NASA social media accounts, and of course, go to www.nasa.gov/New Horizons. I want to thank folks for joining us and witnessing history, space exploration. We have another press conference coming up next Friday on the 24th time, TBD. Thanks for joining us. Science never sleeps.